So it's 11:30, so it's time for me to get started. There's two things I want to mention about, or three things I want to mention. The first one is, anyways, Daryl pointed out to me that this question is on the section 7.4 list of problems. Don't. This is number 37. Don't do number 37. When I looked at it quickly and put it on the list of problems, I somehow had this idea that this thing factored. It doesn't factor. I am not going to give you one like this where the bottom doesn't factor. This is a very painful question anyways, and I would definitely not ask for this on a test or even on a written assignment. It's definitely beyond the scope of this course. For those who are going to be going on to do math majors, maybe you'd see something like this in the future, but yeah. It's definitely too hard. So do not do number 37 from section 7.4. Oh, if you made it work, then if you were able to make it work, then it definitely does work if you know how. But I certainly haven't told you how to do anything anywhere near this, and it's fiendishly difficult.
Some weird stuff because what you end up with the partial fractions is very annoying.
Yeah. The second thing I want to mention, the written assignment is due Tuesday. It's not due today. I think on the version online, the due date said today. That's because I typed up that version before I actually changed the due dates. So don't worry about trying to hand in written assignment today if you don't want to. Third thing is for the, I think it was a third question on the written assignment. You may need to look up some trig identities on the front cover of your textbook. So right inside the front cover of the textbook, there's a list of all the trig identities. There may be one that you need to do that question, which I haven't covered in class, but it's in the inside of the front cover of the textbook. So if you get stuck somewhere, look up those trig identities, it might help you. I think those are all the announcements I have to make for now. Oh, the other thing I wanted to mention, for whatever reason, I have been very spacey today. And one of the things I did in my spaciness was I left the marked quizzes at home. So I don't have those to hand back today. I will have to hand them back next week because we don't have class again until next week. I apologize for that. Anyways, I didn't realize until I got into campus that had happened, and there definitely wasn't time to go home and come back again. So, so you will not have the marked quiz until Tuesday. I apologize, but the marks are up on WebAssign if you want to see what mark you got. Okay. So otherwise, I'm going to move into the slides for today. So this is what I have planned for today's class. I'm going over the agenda now. I want to go over the solutions to last week's group problems because again, I gave out those group problems. I didn't have time to go over, them and all. So I'm going to go over those. Again, just a little bit of review of some of the stuff that we covered last week. I didn't get any minus point cards last class. I can forgot to hand them out. And then there's basically two things I'm covering today. I'm covering section 7.5 and section 7.7. They're both short sections. 7.5 is short because it doesn't actually introduce any new material. It just talks about how we can use the material we've already know to put them together. So to put ideas from different sections together is what's going on in section 7.5. And section 7.7 is short because it is actually significantly easier than anything we've seen in chapter 7 so far. So both of those are short sections. My goal is to get through both of them today. If I don't get through both of them today, that's okay. And rather than having as much time with group problems as I usually do, one of the things I'm going to do is I'm going to be doing this what I call a strategy exercise with the class. We're going to just sort of go over a bunch of problems together from section 7.5. And that'll happen immediately after the break, as I've planned things so far. Any questions about the agenda for today's class? Yes?
Other handout for 7.5?
Oh, yes. I will give those out now. I'll give those out now, yeah. I was going to say I was going to give them out after I went over the group problems from last class, but I'll do it now before I forget, because sometimes I forget otherwise.
Nice.
So here's the 7.5 handouts. And here's the 7.7 handouts, because I know I will at least start the section today, even if I don't finish it. Okay. So, there's two problems I want to go over, which are the group problems from Thursday's class. Just as sort of examples of some of the stuff that we were learning then. So this first one is a partial fractions question, right? You want to evaluate an integral like that, and if you've got an integral of any rational function, the first approach we sort of learned to deal with that is this idea of partial fractions. So we have y over y plus 4 times 2y minus 1. And so the first thing is I'm going to be like, okay, the bottom is already factored, so I know that my partial fractions will look like something over y plus 4 plus something else over 2y minus 1, right? And the next step, then to figure out what a is and what b is. To find those two things, I multiply both sides by this common denominator. When I do that, the left-hand side just becomes y. This a over y plus 4, the y plus 4s will cancel and become a times 2y minus 1. And this one will become b times y plus 4 when the 2y minus 1s cancel. Again, we're multiplying all three things by this denominator here, by y plus 4 times 2y minus 1. So then I've got to figure out what a is and what b is. The easiest way to do it is to plug in numbers for y to make these two things disappear. Well, if I plug in y equals negative 4, the y plus 4 will disappear. So if we plug in y equals negative 4, we get negative 4 over here. 2 times negative 4 is negative 8. Negative 8 minus 1 is negative 9. Let me make sure that looks like a 9 and not a 4. 9a. And then this will become a 0. So negative 4 is negative 9a. So a is going to be 4 ninths. If we rearrange that. Now if I want to figure out what b is, I've got to make this thing disappear. If I want to make this thing disappear, I'm going to plug in y as 1/2. Because if I plug in y as 1/2, 2 times 1/2 is 1. 1 minus 1 gives you 0. So when I do that, the left-hand side is going to become 1/2. Here this is going to be a times 0. It's going to go away. And we've got b times 1/2 plus 4. 1/2 plus 4 is 9 over 2. 4 is 8 over 2. Add 1/2, you get 9 over 2. We want to solve this for b. So b is going to be 1/2 divided by 9 over 2. Flip the bottom and multiply, we get 1 ninth. So a is 4 ninths and b is 1 ninth. So now when we're doing this integral turns into the integral of a, which is 4 ninths, over y plus 4, plus b, which is 1 ninth, over 2y minus 1. I integrate the first one. Again, remember there is a rule for integrating any sort of fraction like that. That's a constant on the top, and just x plus something or x minus something on the bottom. It's going to be that constant times ln absolute value of the bottom. Now for the second one, it's basically going to be the same thing, except when I take ln absolute value of 2y minus 1, I've got to divide the whole thing by 2. Now the reason I have to divide the whole thing by 2, the short answer is because there's a 2 in front of the y, or a 2 in front of the x. The long answer is that what I'm really doing here is I'm doing a substitution. I'm doing u equals 2y minus 1. If u is 2 minus y minus 1, du is going to be 2 dy. So this dy will become a du over 2. And that over 2 there is a thing that appears over here. So again, there's sort of two different ways of thinking about where this comes from. One is sort of just memorizing that rule of how you integrate a number over a number times x plus or minus another number. And the other way is sort of doing the substitution. And both ways yield this answer. Any questions about this example? Anyone confused about what went on here? Again, this is an example of the sort of problem that we dealt with last class, section 7.4. If something like this comes up on the quiz next week, this will be an example. This is about the difficulty that will be on a quiz. Okay. So next I'm going to go over group problem number 2 there. Oh boy, this perhaps not working. This one is also not working. There we go. So number 2, we have the integral from 0 to 1 of 1 over 1 plus cube root of x dx. Now this is a harder example. This is more the difficulty of what's coming up on that written assignment that I handed up last week. And this is harder because it requires 2 different methods of integration. Before I can do partial fractions, I need to do a substitution. And the reason to do substitution here is because I don't have, 1 over 1 plus x and 1 over 1 plus cube root of x. And that cube root of x is annoying. We want it to go away. So what we're going to do to make it go away is we're going to use substitution. And the substitution I'm going to use is u equals cube root of x. Now, if u is cube root of x, du is the derivative of this. Cube root of x is x to the 1/3. The derivative is going to be 1/3 x to the negative 2/3 dx. This I can also think of 1 over 3x to the 2/3. Right? 1/3 x to the negative 2/3 is 1 over 3x to the 2/3. Now what I have here is I don't have this thing floating around in my integral somewhere, so what I'm going to want to do is find a formula for dx in terms of du. So I can replace the dx with something. To do that, I can multiply both sides by the denominator there. So du is 3x to the 2/3. Now, I want that formula to be in terms of u rather than in terms of x. So the thing to recognize is that u is cube root of x, which is the same thing as x to the 1/3. So x to the 2/3 there is actually u squared. So really this is 3u squared du. The other thing I need to think about when I'm doing substitutions, because this is a definite integral, I've got to figure out what are the new limits of integration going to be. So when x is 0, u is the cube root of 0. What's the cube root of 0? It's just 0. Right? So the new lower limit is still going to be 0. Great. When x is 1, u is the cube root of 1, which is 1. So the new upper limit is going to also be 1. So the limits of integration in this context will not change. That's only because they're 0 and 1. If it was integral from 0 to 8, the new upper limit would be 2, because we're taking cube root of 8, which is 2. So this integral will become 1 over 1 plus u, right? The cube root of x will become a u. And the dx will become a 3u squared du. So, now actually I'm just going to rewrite this in a slightly simpler format. Integral from 0 to 1, 3u squared over 1 plus u du. Now we'll notice what we have here is a rational function where the degree of the top is bigger than the degree of the bottom. If the degree of the top is bigger than or the same as the degree of the bottom, before we can even try to do partial fractions, we need to do long division of polynomials. If we don't do long division of polynomials, we won't be able to make the partial fractions work. These partial fractions only work if the degree of the top is smaller than the degree of the bottom. If the degree of the top is 2, the degree of the bottom is 1, we can't use partial fractions. So the next step is to do long division of polynomials. So we do long division, we're taking 1 plus u, and we're putting it into 3u squared. Now 3u squared is really 3u squared plus 0u plus 0. Right? There are these sort of invisible 0 terms here. Oh, I'm going to write the 1 plus u as u plus 1. That's going to make this a lot easier. So first question, the biggest term of this and the biggest term of this. 3u squared divided by u gives you 3u. So u goes into 3u squared 3u times. Multiply the 3u by this, we get 3u squared plus 3u. We're going to subtract 3u squared minus 3u squared is 0. 0u minus 3u is negative 3u. Bring down the plus 0. Then we ask how many times does u go into negative 3u, or what's negative 3u divided by u? It is negative 3. Multiply negative 3 by this, we get negative 3u minus 3. Subtract. Negative 3u minus negative 3u gives you 0. 0 minus negative 3 gives you plus 3. We'll tell you the quotient is 3u minus 3. The remainder is 3. So knowing that, this integral is going to become the integral from 0 to 1 of the quotient, which is 3u minus 3, plus the remainder, which is 3, over the original denominator. And this whole thing I'm integrating with respect to u. And now we can integrate everything. The antiderivative of 3u is 3u squared over 2. The antiderivative of 3 is 3u. The antiderivative of 3 over u plus 1 is 3 ln absolute value u plus 1. And this whole thing has to go from 0 to 1. So then we plug in those limits and subtract. We plug in 1. 1 squared is 1, so we get 3 halves minus 3 plus 3 ln u plus 1 is 2. And absolute value of 2 is just 2. Right, so that's what we get if we plug in 1. Subtract, if we plug in 0, 3 times 0 squared is over 2 is 0. 3 times 0 is 0. 3 times, and here we have 3 times ln 1. Right, 0 plus 1 is 1. Now it turns out ln of 1 is also 0, so this whole thing will also go away. 3 over 2 minus 3 is negative 3 over 2. So the final answer is going to look like this. Negative 3 over 2 plus 3 ln 2. Any questions about this example? Again, this example required a fairly large number of steps, right? First, we had to do this substitution to make the cube root of x into just a u, right? Next, we had to do long division of polynomials to make the top, reduce this top of 3u squared to just a 3, right? Once it was just a 3, then we could actually keep going. And then we had to integrate everything. And now technically, when we're going from this to this, we're actually sort of doing another substitution, right? uv equals u plus 1. Again, I say it oftentimes not, because it comes up so often, it's oftentimes not worth it to show the substitution every time you do that and just sort of remember the rule for how you do that. But, yeah, technically speaking, there is sort of another substitution going on there. Any questions about this example? Yes?
Just that last part about the additional substitution that we did. I missed that.
Okay, so let's suppose I'm gonna go back. Yeah, I didn't actually do it, but I'm just showing you how you could. If you don't want to memorize, so remember one thing I mentioned. There's sort of a rule for how you integrate this, right? It's capital A over little a ln absolute value of x plus b, right? I mentioned that there's a rule for doing this, and you can memorize if you want. If you don't want to memorize the rule, the other way of doing it is with an additional substitution. So in this case, the additional substitution would be if we have 3 over u plus 1 du, right, if we want to integrate this, this additional substitution is v equals u plus 1. So dv is just du. And this will become integral of 3 over v dv. Right? Integral of 3 over v is 3 ln absolute value of v. And v is u plus 1. So that's where this thing comes from. It comes from integrating that using another substitution. Yeah. Yeah. But again, I said usually, I mean, certainly when I'm doing these examples, I'm just sort of using that rule that I showed on the board earlier because it's a lot faster if you use that rule. And some of these problems where you've got like 3 over u plus 1, 2 over u plus 2, 5 over u plus 3, you're doing this almost the same substitution 3 different times in that sort of problem, so you might as well just sort of memorize the rule. But if you're one of these people who doesn't like memorizing rules and prefers to do extra substitutions, this is how you would do that extra substitution. And before you would do the extra substitution, you'd split it up into 3 different integrals. The integral of 3u, the integral of 3, and the integral of 3 over u plus 1. And you'd only do the substitution on that third one. And the other two you can just integrate directly.
Right.
That's the idea. Yeah. But thank you for asking about that because again, I oftentimes skip that step to save time. But yeah, that is technically what's going on. Yes?
Do you want us to split it up into 3 different integrals?
You don't have to. No. If you skip say from here to here on the test, that's totally fine. Yeah. Again, now if it was just if this was the original problem. You know, if I guess that wouldn't come up on the next test, but if it came up on, like, for example, on the exam, and this was the original problem, again, this would sort of be like a chapter 5 problem. And in that case, I'd want you to sort of show what all the steps that you're doing. Basically, if it's one step of a larger problem, you don't have to show as much work. If it's sort of like one single problem that you just start from here, then I do want you to sort of show the work as to how you get from here to here. But yeah, if that makes sense. Yeah. But yeah, in this sort of problem, don't skip straight from here to here, that's fine. Yeah. Yeah. Okay. So that's the group problems from last class. This again is a review of using partial fractions to integrate things. That's sort of the last of the methods of integration we've dealt with. It's the last method of integration we're going to learn, pretty much. So what I'm going to be doing in section 7.5, which is going to be the rest of the class until the break, is going to be talking about what's called strategy for integration, which is basically the question is, if you're given an integral, how do you know which method to use? And this is, for a lot of, like, this is sometimes the hardest part of this, because there aren't really hard and fast rules the way there are for derivatives, right? For differentiation. For differentiation, you've got things like the chain rule, the product rule, the quotient rule. You can see, okay, this one's a quotient, I use the quotient rule. This one's a product, I use the product rule. For integration, it's not that clear cut. You kind of sometimes have to try one method, figure out it doesn't work, and then go back and try another one. It means, one of the things it means is that, you know, I can't ask as many problems on a test because each problem takes a lot longer because sometimes you have to try different methods to approach a problem. But there are some guidelines that are out there that will help you know which method to use. And that's what I'm going to be going over in this section. So for example, if you had an integral like this, 3x over square root of x minus x, the question is then, which method would you use to evaluate it? So that's really what I'm going to be going through in section 7.5 is, you know, just going through a bunch of example problems and sort of talking about how could you get this thing started? Which method would you start with to evaluate this integral? I'm not going to be going through integrals from start to finish in this section. I'm going to be doing more examples and just sort of getting them started and showing you how to, you know, which method you'd use to do something like this. Is there anyone here who feels like they do know which method they'd use to start this integral?
I think it's probably go for substitution to start off with root x.
U equals root x? That is actually correct, yeah. That will work. There might be other ones that would also work. I shouldn't say it. Because that's the other thing too, sometimes equals you can do more than one. That's the one that I would use too. Then start with u equals square root of x. Because then this will become a u. This x will become a u squared. This x will also become a u squared. And this dx will become 2u squared root of u, if you do sort of the rearranging like I did in this example. That I actually just already erased. So this example I can approach like this one I just did. It's an example where I can do a substitution. Once I've done the substitution, it'll turn it into a rational function, so then you can use partial fractions. Again, so far in this course, there's 5 different methods of integration we've gone through. Substitution, integration by parts, trigonometric integration. Now, trigonometric integration is really just how you use substitution and trigonometric identities together, right? When you're doing trigonometric integration problems, you are using substitution, but you're just not only using substitution, you're also using identities, right? That's the idea. Trigonometric substitution, which again is just a special type of substitution, this sort of counterintuitive way of dealing with square roots with an x squared under them, and partial fractions. Again, long division of polynomials is sort of lumped in with partial fractions. Long division of polynomials is the way to make the partial fractions work when the degree of the top is too big. So those are the 5 methods of integration we've learned. Again, the difficult part at this point is determining which one of those 5 methods to perform. If we see a problem, how do we know which one of those to start with? So I'm going to go over a few guidelines to sort of help get an idea of where to start. They're different than the guidelines in the book. If you prefer using the method that's in the textbook, go for it. Use the methods in the textbook. I like to sort of give another approach of thinking about it because for some people one approach will work better, for others another will. But I mean, if you can get to the end of the integration problem, you've done it right. Like there's no wrong way of doing this really, as long as you're able to, get to the end of the integral. So again, I've got 7 different guidelines that I'm going to go through, and each one will sort of say what do you do in each different situation. Any questions before I get into those guidelines? Okay, so the first guideline is that if we have a square root or a 3/2 or a 5/2 power with an x squared inside, that's when you use trigonometric substitution. So for example, if I had this, right, it's a square root with an x squared inside. Or if I had 9 plus x squared to the 5/2, right? It's a 5/2 power. 5/2 power is really square root to the 5th power, right? It's sort of still a square root. It's got an x squared inside. I use trigonometric substitution. So that's the first guideline. This is sort of, trigonometric substitution is the most obvious method to use when it applies. It only applies in very specific situations, and it is very obvious when it does apply, which is when there's an x squared inside a square root or inside a 3/2 or a 5/2 power. So example 1, this is a trigonometric substitution problem. The reason you can tell it's a trigonometric substitution problem is that x squared plus 1 inside a 3/2 power. So again, I'm just going to show how you would get this started. I'm not going to finish it because if I finished every one of these examples, I wouldn't have time to get through all of them. So I'm just going to. So here we have x squared plus 1 to the 3/2 over x dx. So I'm going to, because I have an x squared plus 1, I'm going to use substitution. X is tan theta, which means dx is the derivative of tan theta, which is secant squared theta. So x squared will become tan squared theta. The x on the bottom will become a tan theta. Dx will become a secant squared theta d theta. And then tan squared plus 1 is secant squared. And secant squared to the 3/2 is going to be secant cubed. The halves on the power will cancel off the squareds, and the 3 will make it cubed. Or another way of thinking about it, secant squared is a power of 2. So put it to a power of 3/2. 2 times 3/2 is 3. So simplify to secant cubed theta over tan theta, secant squared theta d theta. And then from there we will keep going. Again, from there we can use, I think the easiest way to deal with the rest of this problem is going to be just write everything in terms of sines and cosines. So write the secant cubed is 1 over cos cubed, 1 over cos squared, tan theta is sine theta over cos theta, and yeah, keep simplifying from there. Any questions about how I knew that this was a trigonometric substitution problem? Or how I got started with these first few steps? Like how I knew that it was x equals tan theta, any of those sorts of things.
Yeah, I think that's my question. How do you just know tan theta was?
Okay, I look for, so I want an identity that looks like something squared plus 1. There's 3 identities I know. Tan squared plus 1 is secant squared, right? 1 minus sine squared is cos squared, and secant squared minus 1 is tan squared. Which of those three identities does it look like? It looks like this identity. It doesn't look like 1 minus something. It doesn't look like something squared minus 1. So the reason I'm using tan is because it looks like something squared plus 1. Yeah. So basically, to make it look like this identity, I have to replace the x with a tan. That's the idea. Yeah. So again, this is where I said that these three identities pretty much need to memorize in order to be able to approach trigonometric substitution problems. Because if you don't know, and the other thing to mention is the first identity and the third one are the same identity, just rearranged.
Yeah, I was just gonna say that.
Yeah. So you don't really need to memorize all three if you're okay remembering that if you move the one to the other side, you get the third one from the first one. Yes, Dimitri?
Do cosecant substitution as well?
No. Anything where a cosecant will work, a secant will also work, it turns out. There is no situation in which a cosecant would work but a secant wouldn't, or a cotangent would work and a tangent wouldn't. Same thing with sine and cosine, but because 1 minus sine squared gives you cos squared, you still need to deal with cosines. But basically, that's sort of why they're called cosine, cosecant, cotangent, because they have the same algebraic properties as sine, secants, and tangents do. They're different trigonometrically, but algebraically they're the same, if that makes sense. I don't know if that... Yeah. Any other questions about this one? Hey, on to guideline 2. Guideline 2 is if we have a composition of two functions. So if we have e to the sine x, square root of 1 minus x cubed, ln x squared, cosine x plus 1. If you ever have one function inside another function, always try to use substitution by making u equal the inside function. The only exception to this rule is rule 1. The only exception to guideline 2 is guideline 1. The only time you don't want to make u be the inside function is if you have something like this. X squared plus 1 to the 3 halves. That's the only time you don't want to make u be the inside function and you have a composition of two functions. Or, sorry, I guess there's another exception which I hadn't thought about when I was making up the slides, which is if you have like something you can expand. So you use like x plus 1 squared, expand that thing. I mean, you can also use substitution, but usually it's easier just to expand it. Yeah, at least always try to make substitution if you have a composition of two functions. So if I have something like this, example 2, I have sine of square root of at. I'm going to start by trying substitution. So I have integral sine square root at. So again, I've got something inside the sine. What's inside the sine is square root of at. So my substitution is going to be u equals square root of at. If we do the derivative of that, this is at to the 1/2, so it's going to be 1/2 at to the negative 1/2. Times the derivative of at. What's the derivative of at? It's just a dt. Right, so again, when I'm taking the derivative of square root of at, I'm using the chain rule here. I take the derivative of the square root part, multiplied by the derivative of the at part, which is just a dt. Now, of course, we don't have this thing floating around in my integral, but what we can do is rearrange this to get a formula for dt in terms of du. So, multiply both sides by 2. Actually, also multiply both sides by square root of at. At to the negative 1/2 is 1 over square root of at. So if we multiply both sides by square root of at, it'll get rid of that on that side. Oh, sorry, du. So 2 square root of at du is a dt. So that means that dt is 2 over a square, and then square root of at, that's just another name for u. So dt can become 2 over a u du. So when I continue this integral, this sine of square root of at will become sine of u. The dt will become 2 over a u du. The thing to mention is because a is a constant, it's not the variable of integration here, Here I'm integrating with respect to t, not with respect to a. There's a reason why when you're writing these integrals, the dt at the end, or the dA at the end, or the du at the end is important. And the reason is because it's telling you which variable you're integrating with respect to. So the 2 over a can come out front. So we have 2 over a integral. I'm going to write the u first. U sine u du. Now, can anyone tell me what the next method of integration I would use to integrate u sine u?
Integration by parts.
Integration by parts, exactly, Dylan. Yeah. So whenever you have like a polynomial times a sine, a polynomial times an e to the x, that's when you use integration by parts. Any questions about this example? How I knew where to use that substitution, how I made the substitution work. Sorry, there should be a box there. These are all the formulas I'm rearranging to get a formula for dt in terms of du. Okay, so third guideline is, and again, this was sort of my thing I mentioned is also kind of the exception to guideline 2, is if we have a polynomial, expand it, unless it appears in the denominator. So there's an exception to this guideline 3 as well, which is if it's in the bottom of a fraction, don't expand it. If in the bottom of a fraction, you want to actually factor it, so you can use partial fractions. Right? If something in the denominator of a rational function, you want to have it factored, because that's factored form is just going to tell you what's on the bottom of the partial fractions. So, but if it's not in the denominator, you want to expand any polynomial. So, this one here, example 3. So if you see this sort of thing, integral x minus 1 over x times x plus 2. The key first step is going to be to expand this thing. We'll get x squared minus 1 times x is minus x plus 2x minus 2. And this will be easier to integrate. Right, that's the idea. Any questions about guideline 3? Again, I haven't finished this one. I've just shown you how to get it to a form where it's easy to integrate. Same with example 2, I didn't finish it. Okay, guideline 4. So this one says if we have an integral which is a product of two functions, or if it's an ln or a tan inverse, then you should try integration by parts. So if you have one function times another function, or if you see an ln in there or a tan inverse in there, those are situations where integration by parts might be useful. Again, there's some example I did earlier where you had an ln in a function and you used integration by parts, even though it wasn't ln of something times something else. It was just like ln of x squared, dx. You still use integration by parts in that situation. It just turns out that integration by parts is the best method for dealing with longs and for dealing with tan inverses. So example 4 here is a situation where we have a logarithm, ln of bracket x squared minus 1 dx. Now you could try to use substitution on this. You try the substitution u equals x squared minus 1. Actually, I'm just going to show you what would happen if we tried that. So again, here we've got one function inside another function, so we might think to use substitution. Well, if we tried that, u equals x squared minus 1, du is going to be 2x dx. So dx is going to be du over 2x. And since u is x squared minus 1, x squared is u plus 1. So x is the square root of u plus 1. So the dx here will become du over 2 square root u plus 1. So if we try to do this with substitution, what we would get is integral ln u du over 2 square root u plus 1. And if you look at this, you can tell this is more complicated than what I started with. So it wasn't a good substitution to do. So that's the one thing to keep in mind, is sometimes you'll try a substitution, but if finding a formula for dx in terms of du makes it more complicated, don't continue with that substitution. Go back and look for another method. And the other method here is integration by parts. So if you want to do this with integration by parts, the key thing is to pick u to be ln of x squared minus 1 and dv to just be the dx. The derivative of u, du, will be 1 over x squared minus 1 times the derivative of x squared minus 1, which is 2x. And if dv is dx, v is just x. Right? The antiderivative of dx is x. So here we're going to get u times v, which is x times ln of x squared minus 1, minus the integral of v du. X times 1 over x squared minus 1 times 2x dx. Oh, sorry, there should be a dx in my du there. So this part I've already integrated. This part still needs to be integrated. And if we look at what this is, x times 2x is 2x squared. This is an integration, or it's a partial fractions problem, right? In fact, actually, we're going to need to do long division first, because the derivative of the top is the same as the derivative of the bottom. Then we'll have to do partial fractions. Now again, I don't have time to go through the long division of partial fractions for this particular example, but this is what would happen in this example. First, do the integration by parts, but if you look at what you've got left here is a rational function. You have a rational function, you have to use long division of partial fractions. Yes, Katie? Sure. Not to, well, actually, I'll try to do it while I'm in the math center today and like write them up. These ones, sadly, I only have, like even in my notes that I have in my office, I only have like the first few steps written up. But I could try to finish these to see what they get, for sure. So guideline 5, here we have an integral which involves only sines or cosines or only secants and tangents. So you have something like sine cubed cos squared or secant cubed tan x or anything like that. Oh boy, that's totally an autocorrect. I typed trig, and for whatever reason it was like, that's not a word, I'm going to change it to truing. Anyways. Anyways, so if it's got like a secant and a cosine, or a tangent and a sine, or a cosecant and a cotangent, turn everything into sines and cosines. That's usually going to be the easiest way of approaching something which has a combination of functions in there. That's not just sines and cosines, or secants and tangents. So this example here, is the next one I'm going to do. So here we have an integral from pi over 4 to pi over 2, 1 plus 4 cotan x over 4 minus cotan x dx. Now this is like, when you first look at it, you're probably a little bit afraid. You'd be like, okay, you know, you've got cotans in there, which is not a function we know how to deal with. You've also got a fraction in there. We've got those 4's in there. How do we deal with it? Well, if you don't know how to deal with it, write everything in terms of sines and cosines. It'll usually make it easier. So when we do that, this cotan will become a cos x over a sin x. This cotan will become a cos x over a sin x. And then here we've got a fraction with the sin x in the denominator, both on the top and the bottom. So what I'm going to do is I'm going to multiply top and bottom of that fraction by sin x. It'll clear the denominators. So here we'll get sin x plus 4 cos x over 4 sin x minus cos x. Okay. It doesn't yet look much better than what I started with, except if you remember back in the section where I talked about substitution, I said one thing that will sometimes work when you're integrating a fraction is to do a substitution, u equals the bottom. And that's, I think, going to be guideline, I think it's going to be guideline 6, the next one. So here I've got a 4 sine x minus cos x there. If I do that substitution, u equals 4 sine x minus cos x, what's du going to be? Well, the derivative of 4 sine x is 4 cos x. The derivative of cos x is negative sine x. Those two negatives will become a positive. And lo and behold, this du is the exact same thing as what appears on the top there. And so this substitution will actually be what allows you to finish the integral. Basically, the bottom will just become a u, the top will just become a du, it'll just be an ln in the end. Again, don't have time to finish it right now, but that's what would happen.
And will be every problem is like that. Everything is fit perfectly.
Not every problem will fit oh, you mean like this? Yeah, that not every problem will fit perfectly. If, for example, one of those 4s was a 3, I just wouldn't give you the problem. So, for example, if it was 1 plus 3 cotangent x over 4 is, if you do that, you'll have a 3 here. Substitution won't quite work. That's not a problem you deal with in this course. One of the things about integrals is that there are mathematicians out there whose job is to integrate things. That's something that mathematicians do because it's a hard enough problem that, it's not fully automated yet. Computers can do a whole bunch of integrals, but there are still ones out there that computers can't do. There are mathematicians out there whose job it is to figure out how to integrate these things. So, so there are very hard integration problems out there. They're just not going to come up in this course because you're I was going to say, it's a first-year undergraduate course. I don't know if they're all first-year students, but anyways, it's not. There's a whole bunch of stuff out here which is like research-level mathematics that I could even write on the board for you what the integral would be. And they're just difficult problems. So
You say some problems can be integral.
there are also functions out there which cannot be integrated. Or what we say is they don't have an elementary antiderivative. So elementary is a fancy word for anything which can be written using the functions we know. So the functions we know are all the trig functions, the exponential function, logarithmic functions, polynomial functions, square roots. And there are things out there which, everything has an antiderivative. It's just not something we can ever find a formula for. And what mathematicians do when they come across something like that is they give it a new name. There are things called Bessel functions, for example, which are antiderivatives of very specific functions. And they're antiderivatives which come up in physics. And they give them a special name because they come up in physics, but we don't have a formula for them. So they give them a new name. Yes?
What's an example of something that isn't elementary?
Integral of e to the negative x squared dx. E to the negative x, that's fine. If I put an x in front of this, I could do that with substitution. But if you have an e to the negative x squared, you cannot, there's no way to do that with substitution, with integration by parts. Trig formulas won't help you. This actually comes up in statistics all the time. And it's really annoying to statisticians that they have to use tables. Or they have to use computers which have the tables memorized. And the reason they have to is because this integral is, those statistic tables in the back of statistics textbooks are the tables of the integral of this guy. For the standard normal distribution. This is the standard normal distribution. Yeah, I think there might be another constant in there now that I think about it, to normalize it. So that the area totally, because the area of this is not exactly 1, it's like pi or something weird like that. You have to put a 1 over square root of pi in front, I think, to make the area 1. Anyways, I can't, I don't teach statistics, which is one of the reasons I've forgotten these things, but...
Is that really necessary to find an elementary function for that? Because I found, as far as I know, normally they will use their calculator to have
exactly.
to have the Riemann sum and add up all the things. So
so it's not necessary to find an elementary antiderivative, but mathematicians get annoyed that they can't. It certainly makes things a lot easier if you could. because then you don't need to rely upon calculators to do Riemann sums. You can actually do at least some of the calculations in your head if you have an elementary antiderivative. Right? Like I say some of them because obviously there's a lot of calculations which you can't do in your head. But one of the things, and again, this is sort of the difference between mathematicians and like everyone else, is that mathematicians abhor numerical methods. There's this thing called numerical methods, which is anything like Riemann sums is an example of a numerical method. The stuff we're covering in section 7.7 is an example of a numerical method. They're called numerical because they give you a numerical answer. They give you an answer which is correct to a certain number of decimal places, but is not exact.
Much more satisfying.
Exactly, and mathematicians are exact. Mathematicians love exact answers, and it's sort of the. And I mean, there is a branch of mathematics called numerical methods, and a whole bunch of applied mathematicians do specialize in it, but it's considered sort of non-mathematical to do things that way. And this is one of the annoying things about integrals. There are some integrals which you can only integrate numerically. There is no elementary antiderivative. There's no actual formula for what you get out of it that you can plug things into. Again, that's sort of, thank you for asking, folks who are asking questions about this. I know you were asking something. Anyways, it's not really part of the material for this course that won't be on the test, but it is it is in the textbook. They talk about that a little bit, about what it means for a function to be an elementary antiderivative, that sort of stuff.
So we didn't need to find it really easy.
Yeah.
Someone should have told me that when I was bombing this.
That elementary, yeah, exactly. No, this is one of these elementary, trivial is another word that mathematicians misuse all the time. Basically, trivial means anything which can be done by a graduate student. Yeah, it's like if you're somebody who has a PhD and you say, okay, the rest of this proof is trivial, you're saying, let the grad students do the work, is what you're really saying. You're not actually saying it's actually trivial, you're saying that I'm too, yeah, anyways, it's part of, mathematical culture is really weird, and I could go on and on about it, and I probably shouldn't because I've got more material to get through. But if anyone has questions about it, I can definitely talk about it like after class or the math center or whatever, but yeah. Okay. So guideline 6 says that if the function we're trying to integrate is a fraction, there's 3 things we can try. First one is partial fractions, right? So if the denominator is a polynomial, we have like an x squared plus 2x minus 1 on the bottom. Try using partial fractions. If you don't have a polynomial on the bottom, but you have some substitution you could do to make the bottom into a polynomial, try that. So that first example where we had a square root of x minus x on the bottom, if we do u equals square root of x, it makes the bottom into a polynomial. That's another thing we can try if we have a fraction. The third thing we can try if we have a fraction is a substitution which will turn, oh wait, sorry, I just said the third one, and I didn't even read the second one. The second one is set u equals the denominator. That's what works here, is u equals the denominator. And setting u equals the denominator is usually the easy way of dealing with fractions. Sometimes it doesn't work, but you should always try it before you try like doing the substitution u equals sine x here, or something like that. So example 6 is an example that we can do using the third strategy. Do a substitution that turns the denominator into a polynomial. Just to show how that happens. Here we have integral dx over square root of x plus x squared of x. So here we're like, okay, it's these square root of x's which are causing problems. So the substitution I'm going to try is u equals square root of x. Du is going to be 1/2 x to the negative 1/2 dx. If I rearrange this, right, x to the negative 1/2 is 1 over square root of x. Multiply both sides by 2 and by square root of x, I get this. And the square root of x there is just my u. So in this situation, if u is square root of x, I can replace dx with 2u squared of u. So this thing will become 2u du on the top. I don't know why I said square root of u, because I was talking too fast. Square root of x is going to be your u. X is going to be your u squared. Square root of x is going to be another u. So that's what I get if I do this substitution. And what you'll notice in this situation is that now this is a rational function. Now this is something I can do with partial fractions. Actually, it turns out this particular one will be easier to do than partial fractions, because if I factor the bottom, I can factor out a u, and I'm left with 1 plus u squared. These u's will just cancel themselves away. I really need to do partial fractions, because the u on the bottom and the u on the top will cancel. I just have 2 over 1 plus u squared, which is basically arctan u. 2 arctan u. Actually, I'm just going to write that out. This is the solution to this one. And u here is square root of x. So the final answer is actually 2 tan inverse of square root of x plus c. Any questions about this example?
On the website, there was an arctan problem, it had a coefficient.
Here, oh, in front of the u?
No, in the integral somewhere, and they said, oh, we just use the formula.
That was one of those formulas I
It's a
mentioned
KX.
at the beginning.
Yeah, it's just I never saw it with the square.
Yeah, I think oh boy, what was the, no, it was like a over a squared plus u squared du, or x, I think you wrote it like this.
Yeah.
And the formula was a over lowercase a tan inverse x over lowercase a plus c.
Yeah, that's something you only figure out.
So you
when
can do
use
this.
when you're actually passing through the problem.
Yeah, and you can actually, exactly, so like, and again, I would suggest just memorize this formula, put it as one of your antiderivative rules and just memorize it. It's a lot easier than trying to do a substitution, and it comes up often enough that the chances that you will see it on either the test or the final exam. So, and if you do memorize it and not actually write out the steps in between, I'm okay with that. Again, you can do it with substitution. The substitution you have to do is u equals x over a. It's a weird substitution to do in the first place. So I would say it's easier just to memorize the formula, but that's where it comes from. So does that answer your question, Danielle?
Yeah,
Yeah.
thank you.
Great. Okay, so last guideline is this sort of if all else fails situation, and if all else fails, try to use algebra to rewrite the integral. So an example of this, is something like this. E to the 2t over 1 plus e to the 4t dt. The annoying thing here is you have both an e to the 2t as well as an e to the 4t. And so you're not sure whether you should do substitution u equals e to the 2t or substitution u equals e to the 4t. And so one thing we can do to rewrite this integral is to recognize that e to the 4t is actually e to the 2t squared. Because 2t times 2 is 4t. The other thing we could do is I can think of the e to the 2t as e to the t squared if I wanted to. But if I think about the e to the 4t as this, then I can see that u equals e to the 2t is the substitution that makes the most sense. So if u is e to the 2t, du is 2 e to the 2t dt, right? That's what the derivative of e to the 2t is. Here we have an e to the 2t dt, so e to the 2t dt is du over 2. So the integral is going to become 1 over 1 plus u squared times du over 2. Right? The reason it's 1 over 1 plus u squared is because the e to the 4t is e to the 2t squared, and the dt is just du over 2. And again, from there on, 1 over 1 plus u squared, that's just another tan inverse situation. These tan inverses come up in these weird situations sometimes, and you don't even expect it to pop up. It pops up, you're like, oh, okay, arctan. That's how I solve this problem. Any questions about example 7? Okay. Yes, Katie?
Why is there a 1 on top?
There's a 1? Because really there's a 1 times this. So this thing becomes the du over 2. I mean, I could write it this way if I wanted. If you prefer this, you can totally write it that way. I just don't like writing a fraction on top of another fraction. So if I have a number here which is a fraction, I just move it out here and put a 1 over. But yeah, there's two ways of writing the same thing. Yeah. Okay. So the last thing I'm going to cover before the break is 7.5.2, which is called Applied Integral Problems. This is something that's not in section 7.5 in the textbook, but I'm inserting it here because I figure this is the best way to talk about, best place to talk about it. I started to cover this in section 7.1. If you remember in section 7.1, there was like an area problem I did using integration by parts. 7.5.2 is all about sort of how can you use the techniques we've learned in chapter 7 to solve chapter 6 problems. So chapter 6 problems are things like area problems, volume problems, work problems, average value problems. One thing I'm going to mention is anything which is a chapter 6 problem which is going to come up in chapter 7, like is going to come up in the next test, is going to be an easy chapter 6 problem. It's not going to be like one of those ones where like the cross sections are equilateral triangles, that sort of thing. So if you look at the ones that are on the handout, those are sort of about the difficulty. And I've made up 8 problems that are this sort of situation where we use chapter 7 techniques to solve chapter 6 problems. The last one on there is the only one that's more difficult than, so of the 8 problems I put on the handout, the first 7 are the difficulty you might see on the test. The 8th one is a sort of assignment difficulty rather than test difficulty. So again, on the next test, there'll be one word problem that will come from chapter 6 that will require the use of a chapter 7 integration technique to solve it. It could be an area problem, a volume problem, an average value problem, or a work problem. And again, if it's a work problem, it's usually going to be an easy work problem, like something like this is the formula for the force. Find the work done and moving it from here to here. In which case, you basically just integrate that formula for the force. So I'm going to do 2 examples of this. The first one is actually an example that came up in section 7.1 that someone put on my point card saying, I want you to go over it later. I inserted it in here because this is where it really fits. So here, we want to calculate the volume of the solid generated by rotating the region bounded by y equals ln x, y equals 0, and x equals 2 about the x-axis. Well, this is what the graph of y equals ln x looks like. Y equals 0. There's this blue line here. Y equals 0. X equals 2 is here. And this intersection points at 1, 0. Where L at x and y equals 0 intersect, it's when x is 1. So, I'm trying to rotate this thing about the x-axis. So I'm going to take a slice. A slice of this thing will look like that red piece there. And if I rotate it about the x-axis, well, the shape it gives me is a disk, right? The radius of the disk is this distance there. The radius of the disk is the distance between ln x and 0. Distance between ln x and 0 is just ln x. Right? So the radius of the disk is ln x. The area of the disk is therefore going to be pi times ln x squared. Right? The area of a circle is pi times the radius squared. So, and if you remember, when you're calculating volumes, what you want to integrate is the area. You integrate the area dx. So I have a formula for the area. So now I've got to integrate it with respect to x. And this integral is going to go from this point, which is 1, to this point, which is 2. Now this is also something I'm going to have to integrate by parts. And the reason I'm going to have to do integration by parts here is because there's an ln x in there. I mentioned that if you ever have an integral with an ln x, it usually means you have to do integration by parts. I'm going to pick u to be ln x squared, and the dv is going to be what's left, which is pi and dx. dv, I don't know why I x. So du, the derivative of ln x squared, is 2 times ln x times the derivative of ln x, which is 1 over x dx. If dv is pi dx, v is pi x. I'm doing the antiderivative of pi gives me pi times x. So, when I do integration by parts, I'm going to have u times v, which is ln x squared times pi x. This thing's got to go from 1 to 2 minus the integral of v, which is pi x, times du, which is 2 ln x, 1 over x dx. So I'm going to plug in the 2 and the 1 in here. It's going to be ln 2 squared times pi times 2 minus ln 1 squared times pi times 1. And here, I'm going to simplify first. The pi is a constant, it can come out front. This x, so the 2 is also a constant, it can come out front. The x and the 1 over x will cancel. And so I'm just left with ln x dx. Now there's two things and this goes from 1 to 2. Now there's two ways I can deal with this thing that's left, this integral of ln x. I can do integration by parts again if I want, or I can have the integral of ln x memorized. And I'm just going to show you what would happen if we had the integral of ln x memorized. So ln 2 squared is just going to be ln 2 squared. I can't really do much with that. This is just a 2 pi. Pi times 2 is just 2 pi. ln 1 is 0. So this whole term here with the ln 1 in it goes to 0. And here, the integral of ln x is x ln x minus x. This is one of those integrals that's in your textbook on sort of the table of integrals in the back. And if you want to, you can memorize this. And every time you have to integrate ln x, you can just write x ln x minus x and not have to do the integration by parts again. And the last step, I need to plug 2 and 1 into that last thing. So here I'm going to have I'm just going to write this, 2 pi ln 2 squared. Here, when I plug in a 2, I'll get 2 ln 2 minus 2. When I plug in 1, I get 1 ln 1 minus 1. And I can simplify that if I want, by making this ln 1 is 0, or I can just leave it like that. This is the volume of this shape when I take this region and rotate it about the x-axis. So the idea is it's a volume problem which requires integration by parts in order to evaluate it. Any questions about this example? Okay. So example 9 is a work problem. Here it says if a positive charge is placed at x equals 2 and a negative charge at x equals negative 2 on the x-axis, then an electron on the axis will experience a force pushing it to the right. And here's a formula which will give you the magnitude of that force. We want to figure out what does the work done by this force that moves the electron from x equals negative 1 to x equals 1. So the key thing in this problem is just to remember that work is the integral of the force. Right? This is sort of something I mentioned earlier. If you want to calculate the work done, you can integrate the force with respect to x. Again, this requires the force to be expressed in terms of the distance, in terms of x, in order to do this. So here we'll have the integral from negative 1 to 1 of 20x over this thing, x to the 4th minus 8x squared plus 16. Now, in order to actually do this integral, we're going to need to factor the denominator. So I'm just going to write that out over here. This thing, I want two things that add to give me negative 8, multiply to give me positive 16, or negative 4, and negative 4. So this factor is x squared minus 4, x squared minus 4. Now the reason it's an x squared and not an x is because it's an x to the fourth and it's an x squared, rather than being an x squared and it's an x. X squared minus 4 then factors as x minus 2 times x plus 2. This one also factors as x minus 2 times x plus 2. This is an x minus 2 squared times an x plus 2 squared. So, when I do my partial fraction decomposition, I'm going to need to have something over x minus 2, something over x minus 2 squared, something over x plus 2, and something else over x plus 2 squared. And if I multiply both sides to clear denominators, on the left I'll get 20x, on the right I'll get a x minus 2 x plus 2 squared plus b x plus 2 squared plus c x plus 2 x minus 2 squared plus d x minus 2 squared. Again, I'm skipping some steps here to show the outline of this problem, partly because, I'm about 10 minutes behind where I wanted to be in the schedule. So here, in order to figure out what a, b, c, and d are, we're going to have to plug in different numbers for x. So if we plug in x equals 2, the 20x will become a 40. This first thing will go away because it's got an x minus 2 in it. The second thing will become a 16b. X plus 2 is going to be 4. 4 squared is 16. This will go away. This will go away. They both have x minus 2's in it. So 40 is 16b. 40 divided by 16 is 2.5. Actually, I'll write it as 5 over 2. Then I can try and plug in x equals negative 2. See what happens. Well, the left-hand side will become a negative 40. This thing has an x plus 2 in it, it'll go away. This thing has an x plus 2 and it'll go away. This thing has an x plus 2 and it'll go away. Negative 2 minus 2 is negative 4. Negative 4 squared is 16. So negative 40 is 16d. D here is going to turn out to be negative 5 over 2. So I'm still not finished. I've got b and d. I don't have a and c. So what I can do is I can try plugging in different numbers for x. Let's say I plug in x equals 0. See what happens. Well, the left-hand side becomes a 0. This 0 minus 2 times 0 plus 2 is negative 2 times 4, which is negative 8. 0 plus 2 is 4 squared, so I have a 4b. 0 plus 2, 0 minus 2 squared is an 8c. 0 minus 2 is 4, I have a 4d. Okay. Since I know that b is 5 over 2, 4b is 10, 4d is negative 5 over 2, which is negative 10. So really, 0 is negative 8a plus 8c. This still doesn't tell you what a and c are, so I'm going to need another equation. To get that other equation, I can try plugging in x equals 1. If I plug in x equals 1, get 20 on the left. 1 minus 2 is negative 1. 1 plus 2 is 3. Negative 1 times 3 squared is negative 9. So 20 is negative 9a. Here, 1 plus 2 is 3 squared is 9. So plus 9b. 1 plus 2 is 3. 1 minus 2 is negative 1. Negative 1 squared is 1, so 3c. And d, 1 minus 2 is negative 1. Negative 1 squared is 1 plus d. And now I can fill in what b and d are. b is 5 over 2. 9 times 5 over 2 is 45 over 2. Minus 5 over 2 gives you 40 over 2. So, actually, 9a plus 45 over 2 plus 3c minus 5 over 2. 45 over 2 minus 5 over 2 turns out to be 20. Subtract 20 from both sides, I get 0 equals negative 9a plus 3c. Anyways, if I rearrange this, divide both sides, move the negative 8 out of the other side, I get 8a equals 8c, a equals c. Right, so I know a and c are the same. If a equals c, this means 0 is negative 9c plus 3c. So 0 is negative 6c, which means c is 0. And since c is 0 and a equals c, a is 0. So it took a lot of work, but I was able to figure out that both a and c happen to be 0. This isn't the only way of doing this. I could have, for example, expanded this whole thing on the right, equated coefficients. There probably was some trick for showing that a and c were both 0 by like taking the derivative of both sides. Sometimes you can do things like that, and that'll actually work out to show that both a and c are 0. Anyways, they are both 0. So this integral here, knowing that a and c are both 0, will become the integral from negative 1 to 1. So the b is 5 over 2. So I have 5 over 2 over x minus 2 squared plus negative 5 over 2 over x plus 2 squared dx. Integrate the first one. That's going to give you negative 5 over 2 over x minus 2. Integrate the second one. That's going to give you positive 5 over 2 over x plus 2. Again, those are just, I'm just using those formulas for how you integrate a number over x minus something to the power of n. Basically, this negative sign comes from the fact that this is a negative 2 power. It goes up by 1 to become a negative 1 power, which means you divide by negative 1, which is where this negative sign comes from and why that negative sign goes away. This whole thing we have to plug in from negative 1 to 1. So the final answer we're going to get is going to be negative 5 over 2 over 1 minus 2, which is negative 1, plus 5 over 2 over 3. That's what you get when I plug in 1. Plug in negative 1, I'll get negative 5 over 2 over negative 3, plus 5 over 2 over 1. Anyways, and I could simplify that if I wanted to. I'm realizing that this particular problem is one that's, I'm not going to give you an integral this hard on the test. The amount of time it takes is just too much. I've definitely taken up more time than I planned to with this integral here. So again, it's 12:48. Take a break until 12:58. After the break, I'm going to do a little exercise involving strategy stuff, and then I'll start section 7.7.